Well, hello again, dear students. We were doing chemical properties of aldehydes and ketones, so we'll continue with that. In the last session, we did nucleophilic addition reaction. In today's class, we'll be doing nucleophilic addition, nucleophilic addition followed by elimination of water molecule. Followed by elimination of water molecule. Well, as far the set of these reactions are concerned, they are one of very important reaction because you will get a distinguished test in this. You'll get some very important questions from these type of reactions. Well, before starting with these reactions, I would like to tell you one thing, that the nucleophile we'll use in these reactions are ammonia derivatives. Suppose I've got either an aldehyde or a ketone, and I'm drawing it like this because both of them, they have got a carbonyl group. So this is the carbonyl group of aldehyde or ketone. The nucleophile in this case is ammonia derivative. You know very well that ammonia is NH3. Now what I have done, I have removed one of the hydrogen and I have substituted it by a group. I am representing that group by Z. It can be any group. You will see in the reactions that Z can be like OH or another NH2 group. So when I am carrying out this reaction has to be carried out in slightly acidic pH. What will happen? The H2 from the nucleophile will combine with oxygen of the carbonyl group. They will come out as H2O. You will get compound like this. So these reactions are nucleophilic addition followed by elimination of water molecule. A question comes to our mind, why we are using acidic pH? Why the rate of reaction increases in the presence of an acid? Well, in this case, I would like to tell you one thing, that the nucleophile we are using is not negatively charged. Kindly pay attention to what my words, because this is the answer of the question. Why we use slightly acidic pH? Because the nucleophile is not negatively charged in this case. The nucleophile is ammonia derivative. That means the nucleophile is a weaker nucleophile. Why it is a nucleophile? Well, let us have a look at this. This is the carbonyl group I have got. The pi electron will move toward oxygen will become negative and carbon will acquire a positive charge. And if I have a look at this compound is like this. And here you have got Z and it has got a lone pair of electrons. This nucleophile. Although it is not a negative nucleophile, but it is a nucleophile because it has got a lone pair of electron and it has a tendency of donating that lone pair of electrons to a carbocation. So it can donate it to this carbocation. Now since it is a weaker nucleophile, the rate of reaction is slow. By maintaining slightly acidic pH, I increase the positive charge on the carbocation. Let me show you how the reaction proceeds. Well, initially what happens? Pi electrons are coming toward oxygen has become negative. H positive from the catalyst will attack on this oxygen. As soon they will attack on this oxygen, you will get a compound like this. And in this compound, the positive charge on carbon will be stronger. It will become stronger. This positive charge becomes so very strong that it becomes easier for even a weaker nucleophile to attack. So this nucleophile will attack on this carbon very easily. See, when you want a nucleophile to attack on a carbocation, the two things which you can do is either increase the negative charge on the nucleophile or increase the positive charge on the carbocation. This is what we are doing here. We cannot increase the negative charge on the nucleophile, but we are increasing the positive charge on the carbocation. The positive charge increases to such an extent in this acidic medium that carbocation becomes capable of attracting even weaker nucleophiles. So it will attract this nucleophile will attack easily and will form a compound like this. form compound like this. H and OH will come out as H2O. Then you will get a compound like this. This compound will lose H positive ion and you get a stable compound that is NZ. CH positive is a catalyst. It was used from here, your reaction is starting. So you'll see that it was used in the first step and regenerated in the last step. So by maintaining slightly acidic pH, we increase the positive charge on the carbocation of aldehyde and ketone. So it becomes easier for a nucleophile to attack. Again, I'm dictating the answer of this question. Many a time the question is asked why during nucleophilic addition followed by elimination of water molecule of aldehyde and ketones, slightly acidic pH is maintained. The answer is the nucleophile in these reactions are ammonia nucleophile. They are not negatively charged, so they are weaker nucleophile. They have their nucleophility due to the presence of lone pair of electrons. To increase the rate of a reaction, we maintain slightly acidic pH. As the H positive ion from acid will combine with the carbonyl group, they will increase the positive charge on carbonyl carbon. So it becomes easier even for a weaker nucleophile to attack on it. And so the rate of reaction will increase. Now we'll see the reactions in this part. First reaction we'll see addition of hydroxyl amine. I've got a compound like this. It can be either an aldehyde or a ketone. I'm reacting it with hydroxylamine. In the presence of an acid, H2O will come out. I will get compound like this. This compound is known as an oxime. If you are preparing it from aldehyde, we call it aldoxime. And if you are preparing it from ketone, it is known as ketoxime. So it can be either an aldoxime or a ketoxime. Second, we'll see addition of hydrazine. Here I have an aldehyde or a ketone molecule. I'm reacting it with hydrazine. In hydrazine, you can easily see that Z is another NH2 group. So H2O will come out and you'll get compound like this. This is hydrazone. So the compound we are getting from hydrazine is hydrazone. Next is addition of 2,4 dinitrophenyl hydrazine. Two comma 4 dinitrophenyl hydrazine. Now let us have a look at this compound. Here I have aldehyde or ketone. I am reacting it with 2,4 dinitrophenyl hydrazine. Here you will have NO2 group and on this position also you will have NO2 group. This is 2,4 dinitrophenyl hydrazine. In the presence of acid, H2O will come out and you will get a compound like this, C double bond N single bond NH. Then a benzene ring attached to this, which will have NO2 group at second and fourth position. This is an orange colored compound, orange PPT you will get. This compound is 2,4 dinitrophenyl hydrazone. So this is what you are getting, 2,4 dinitrophenyl hydrazone. Well, this reaction is used as a test to detect the presence of aldehydic and ketonic group. I told you one more test, that is addition of sodium bisulfite. This is the second test, and this is the one which is very important for you, because many a time a question is asked based on this. Suppose you have been given a compound like CXHYO. Single oxygen means it can be either an aldehyde or a ketone or an ether or an alcohol. But if it says that it gives positive DNP test, positive DNP test means it forms orange colored precipitates on reaction with 2,4 dinitrophenyl hydrazone. That means it is neither an alcohol nor an ether. It is either an aldehyde or a ketone, because only aldehyde and ketone form this additional complex orange precipitates. So this is what you have to remember. After this, we'll move on to the next addition, that is addition of semi-carbicide. Here I have aldehyde or ketone. I am reacting it with semi-carbicide. The compound is like this. In the presence of H positive. See, here you can see that you have two hydrogens which can be used to come out as H2, or we can say we have two nitrogens which can act as a nucleophile. Either this nitrogen can act as a nucleophile or this nitrogen can act as a nucleophile. Now in this case I want to tell you that this, I am marking it as number 1, I am marking it as number 2. It is number 2 hydrogen that will attack as a nucleophile, not number 1. The question comes to our mind, why? First I'll show you the compound. H2O will come out. You will get a compound like this, that is N, single bond NH, CO, NH2. From semi-carbicide, you are getting semi-carbazone. Well, the question which I am telling you is there in your textbook also. And it is one of a very important question. Many a time it is asked, give reason why the nitrogen which is attached to carbonyl group does not act as a nucleophile. That means this nitrogen does not act as a nucleophile. Why it is this nitrogen which is acting as a nucleophile? Well, for that we'll see the structure of semi-carbicide in detail. The structure is like this. The pi electron move toward oxygen, so oxygen acquires a negative charge and carbon acquires a positive charge. Since carbon acquires a positive charge, it becomes electron withdrawing in nature. So it withdraws electrons from the neighboring nitrogen atom. That means the lone pair of electron of these neighboring nitrogen atoms are in continuous resonance with this carbon. I'll show you those resonating structures also. I can draw it like this: NH2, C, O negative, double bond NH, single bond NH2, or NH2, double bond carbon, oxygen, which is negative, NH, single bond NH2. Well, this is your exercise question. In that question it is asked, there are two NH2 group which can act as a nucleophile. The one which is attached to the carbonyl group cannot act as a nucleophile. Give reason why. The answer is that carbonyl group is electron withdrawing. So it withdraws electron from neighboring NH nitrogen atoms. So the two neighboring nitrogen atoms, they donate their lone pair of electron to carbonyl group. So their lone pair is in continuous resonance with the carbonyl group. Hence it is not freely available to be donated. Hence they cannot act as a nucleophile. The another NH2 group which is not attached to carbonyl group is not under any such resonance. So it can donate its lone pair of electron and will act as a nucleophile, leading to the formation of semicarbazone. After that, addition of amines. Addition of amines we'll see. Addition of amines. Now, suppose the carbonyl group I have got is like this. I am reacting it with NH2R in the presence of an acid. H2O will come. I will get compound like this. This compound is an amine, also known as Schiff's base. So these are the compounds we'll get, and these are the nucleophilic addition followed by elimination of water molecule. After that, we'll see this next type of property, that is oxidation. Third is oxidation. Dear students, I told you one thing beforehand when we were talking about alcohols in function group 1, that if you oxidize alkanes, they'll give you alcohols. Alcohols on oxidation gives you aldehyde and ketones. Aldehyde and ketones on oxidation gives you carboxylic acids. So in these reactions which we are going to do here, aldehyde and ketone will undergo oxidation and they will give you carboxylic acid. First thing I want to tell you that in case you want to detect the presence of an aldehyde or a ketonic group, you will do DNP test, as I told you a couple of minutes back. But if you want to differentiate, if you want to know whether it is an aldehyde or a ketone, see, if there is a single oxygen, you know it is either an aldehyde or a ketone. But whether it is an aldehyde or a ketone, how you will come to know? You will come to know by these reactions, which I am going to tell you. Here you will see a test to differentiate between aldehyde and ketone. So let us first have a look at aldehyde and ketone. If I talk about aldehyde, the general structure, as you know very well, is like this. And ketone is like this. Well, since aldehyde has got a hydrogen attached to alpha carbon, that is the function group, so it can easily undergo oxidation. It has got hydrogen attached to alpha carbon, it will easily undergo oxidation and will form a compound like this, that is carboxylic acid. Whereas in case of ketone, it is not like this. You have to break this carbon-carbon bond to form a carboxylic acid. That means aldehydes can undergo oxidation easily, but ketones, they does not. That means weak oxidizing agents can oxidize aldehydes, but they cannot oxidize ketones. So this is what we are going to do here. We are going to oxidize them by weak oxidizing agent. You will see that aldehydes will undergo oxidation, ketones will not undergo oxidation. Therefore, these reactions can be used as a test to differentiate between aldehyde and ketone. First, I will tell you oxidation by tolerance reagent. Well, when I am saying by tolerance reagent, what is tolerance reagent? It is actually ammonical silver nitrate solution. It is ammonical AgNO3. Now let us have a look at the reaction. I've got a compound that is an aldehyde, RCHO. I am reacting it with tolerance reagent. So it will react with the tolerance reagent, which is like this. And no doubt this tolerance reagent is alkaline. It is basic in nature. It will oxidize aldehyde to carboxylic acid, that is COONH4. I will get 3 moles of NH3. I will get 2 moles of silver, and along with that I will get a molecule of H2O. See here in this reactant you can see that you have got 4 ammonia molecules. Out of those 4, one will combine with this aldehyde, one oxygen will come from OH. You will get RCOONH3 plus H, that is NH4. So ammonium salt you will get. Rest of the 3 NH3 will come out. Silver in this case is in +1 oxidation state because you have got +1 oxidation state, +1 charge on the square bracket, on the whole of the compound. OH negative is counterbalancing that charge. So that means that positive charge is coming from silver because ammonia itself is neutral. So here the oxidation state of silver is +1, here the oxidation state of silver is 0. That means Ag is undergoing reduction, so it is oxidizing aldehyde. This silver will settle down at the bed of the test tube. When it will settle down at the bed of the test tube, if you see, you can see your face in the glass of the test tube because it is acting as a mirror. Inside you have got a coating of silver. That's why we call it silver mirror. Silver mirror. So aldehydes can easily reduce tolerance reagent, or we can say aldehydes can easily undergo oxidation by tolerance reagent, reducing that tolerance reagent to silver and forming silver mirror. So aldehydes gives positive silver mirror test, but ketones they does not. Now again, if a question is given to you, there is a compound with molecular formula CXHYO. It gives positive DNP test. Positive DNP means it can be either an aldehyde or a ketone, not an alcohol or an ether. And it gives positive DNP test. That means it is an aldehyde, not a ketone. So this is how you can conclude whether it is an aldehyde or a ketone. Second test also, the second reaction that can also be used as a test to differentiate between aldehyde and ketone, that is oxidation by Felling's reagent or Benedict's solution. Well, if I talk about Felling's solution or Benedict solution, both of them they have got nearly same composition. Both of them they have Cu2 positive ion like CuSO4. Both of them they are alkaline. They have a base like KOH or NaOH. The only thing is in Felling's solution the complexing reagent which makes the complex is citric acid, whereas in Benedict solution it is tartaric acid. And it does not pose any, means it does not give any change to the chemical reaction. So same reaction can be used for both the reagents. Now here in this case, suppose I have an aldehyde RCHO. I have got 2 moles of Cu2 positive plus 5 moles of OH negative alkaline medium. It will oxidize aldehyde to carboxylic acid, that is RCOO negative, or this is what I am getting, RCOO negative plus Cu2O plus 3H2O. This Cu2O will settle down at the bed of the test tube as brick red precipitates. So aldehydes will undergo oxidation by Benedict solution or Felling's solution, giving you brick red precipitates, but ketones they does not. So this reaction can be used as a test to differentiate between aldehyde and ketone. And this is all about oxidation of aldehydes. Now we'll see oxidation of ketones. Oxidation of ketones. As I told you that oxidation of ketones cannot be carried out by a weak oxidizing agent like Felling's solution or Benedict solution or tolerance reagent. We have to use a strong oxidizing agent like KMnO4. KMnO4 in alkaline medium. Here it will act as a strong oxidizing agent because we need to break the carbon-carbon bond in this case. Now suppose you have got a symmetric ketone. You have got a ketone like CH3, COCH3, and you are oxidizing it. The oxidizing agent again is KMNO4 in alkaline medium. The carbon-carbon bond can break from any of the side, no matter whether it breaks from side A or it breaks from side B. From any of the side, if this bond breaks, on one side you will get 2 carbon, on another side you will get 1 carbon. So what you will get? You will get 2 different carboxylic acid, that is CH3COH, and you will get HCOOH. My dear students, no matter whether the bond breaks from side A or from side B, in both the cases, on one side you will get 2 carbon, on another side you will get 1 carbon. The carboxylic acid containing 2 carbon is acetic acid, as you can see, and the carboxylic acid containing 1 carbon is a formic acid. So you'll get a mixture of acetic acid and formic acid. What about a non-symmetric, unsymmetric ketone? Now suppose I got a ketone that is CH3, CH2, CO, CH3. If I oxidize this compound, again, the bond can break from side A or it can break from side B. Well, if it breaks from side A, you will get 2 carboxylic acid with 2 carbon each. That is, from A, you will get 2 moles of CH3COOH. From side A, if it is breaking, on both the sides you are getting 2 carbon, so you will get 2 moles of acetic acid. But if it is breaking from side B, if it breaks from side B, on one side you'll get 1 carbon, on another side you'll get 3 carbon. So you'll get a molecule of propanoic acid and formic acid. Now the question comes to our mind, where from this bond will break? Well, in that case, the oxidation of ketone is going to follow the Pope's rule. Pope's rule. According to this rule, during oxidation of an unsymmetric ketone, the carbon-carbon bond breaks in such a way that the carbonyl group, this group, will go with the smaller alkyl group. Well, in this case, if we see this is an ethyl group, this is a methyl. So methyl is a smaller one. That means the carbonyl group will go with the methyl group. That means the bond will break from side A. So this will be the product you will get. So according to Pope's rule, during oxidation of an unsymmetric ketone, the carbon-carbon bond breaks in such a way that the carbonyl group goes with the smaller alkyl group. This is all about the oxidation reaction of aldehyde and ketone. We will see their reduction reaction. So fourth reaction is reduction. Again, I would like to remind you one thing, that alkane on oxidation gives you alcohols, alcohols on oxidation gives you aldehyde and ketones. So if I reduce aldehyde and ketone, I can either get back alcohol or I can get alkane. So we'll see what we'll get. First we'll see reduction to alcohols. This we have already done in the preparation of alcohols. Reduction to alcohols. And I have told you that we can use lithium aluminum hydride or NaBH4. In alcohols and phenols, I told you the difference between lithium aluminum hydride and sodium tetrahydrogen borate. For reduction of aldehyde and ketone, we can use this reagent. Kindly, if you want to know the difference between LiAlH4 and NaBH4, kindly see those videos of alcohols and phenols. In the preparation of alcohol, you will get in detail what's the difference between LiAlH4 and NaBH4. Well, in this case, I will just tell you that if you have got an aldehyde on reduction with NaBH4 will give you an alcohol, and that alcohol is primary 1 degree alcohol. Likewise, a ketone will give you a secondary alcohol. So aldehydes on reduction will give you primary alcohol, ketone on reduction will give you secondary alcohol. We'll see reduction to alkanes. When I'm saying reduction to alkanes, in this case I'll be using strong reducing agent. So first reduction I'm telling you by zinc amalgam and HCl. Now in this case, no matter whether you got an aldehyde or a ketone, I'm giving you an example of a ketone. Acetone I have got. From this reaction we'll get 4 nascent hydrogens that has come by the reaction of zinc amalgam and HCl. You will get compound CH3, CH2, CH3 along with H2. So the compound you are getting is a propane. So here you can see reduction to alkane. This reduction process known as Clemenson's reduction. This is Clemenson's reduction. Next reduction we'll see by hydrazine. Reduction by hydrazine. Hydrazine we have already seen in nucleophilic addition followed by elimination of water molecule. And there I told you that compound is like this, NH2 single bond NH2. I told you one more thing, that these reactions they proceed in acidic medium. So H2 and O will come out as H2O. You will get compound CH3, CH3 double bond and single bond NH2, that is hydrazone. Well, in this case I would like to tell you one thing, that if you react this hydrazone with a base, that can be either KOH or you can use glycol. Glycol again is ethane 1,2-diol that will act as a base. Nitrogen will come out. And when nitrogen will come out, you'll again get propane, that is CH3, CH2, CH3. This is what you'll get. So propane is what you are getting. This reduction process is known as Wald-Kirchner reduction. So Wald-Kirchner reduction is what you're doing. Third reduction process we can use by HI. Well, HI again is a strong reducing agent. Again I am giving you the example of propanone. I am reacting it with 4 moles of HI. I will get compound CH3, CH2, CH3 plus H2O plus 2I2. So HI again is a strong reducing agent, will reduce aldehyde or ketone to their corresponding hydrocarbon. Student, this is what we were supposed to do in today's class. We are left with another type of reaction, the 5th type of reaction, that is reaction with base. And those reactions, they are really very important because you'll get aldol condensation, Cannizaro's reaction in that. So we'll be doing that in the next class. I just want to tell you one thing, that please revise all your reactions from these videos, because the more revision of organic chemistry you will do, the more comfortable you will become in organic chemistry. Revision is a key for organic chemistry. If you are not revising your reactions, you will forget them. So kindly do that, allot some time for the revision of these reactions. At least one day in a week, you have to revise these reactions. Go through the videos. I'm explaining each and everything. Just see these videos at least once in a week. That will help you in a great way in understanding of organic chemistry. This is all we have for today. Again, I would request you to subscribe this channel so that you will get all the lectures on time and notification also. Thank you very much. Thanks a lot for joining. Thanks.